Hmm. So here we are. This is my IDE, or Integrated Development Environment, for my microprocessor. I call it Virtue, for Versatile Instruction Rapid Tractable Update Engine. And so I've been working on this in JavaScript. As you may be aware, JavaScript runs on everything. It runs on the notebook, runs on the phone, the tablet, the laptop, the desktop, Microsoft, Windows, Linux, Macintosh OS. They all run JavaScript. They kind of need to be compatible with each other, and so the web languages, JavaScript, HTML, and CSS, have become ubiquitous. They're all over the place. I don't know where else they've gone. It's everywhere. And so you write it once, it works on everything. And it doesn't seem like it's going to change anytime soon. So I use JavaScript for everything. I have code that writes Verilog in JavaScript. It just prints out the code into a text field. You just, what is it? It's like document dot enter HTML, and you just add to what's already there, and you can put carriage returns and stuff with a PRE tag in HTML, and do all the stuff you want. But graphics are a different matter. I have a canvas tag. I have this canvas tag in JavaScript, and so I got a 720p image here. These characters are 16 by 16 pixels, and they're the right size for pretty much anything you want to do on a game console. Like an Atari or a Commodore or whatever. But since it's JavaScript and it's a canvas tag, I have 24-bit color, and I can remember those old computers with the cursor, that looked like this, a little square cursor that would move around and select one character. Typically, you only have a choice between 1.5 colors. you would have well, on the Atari it was like blue in the background, and it had a lighter blue color for the text. But I can make these colors whatever I want. And soon I'm going to have this on an FPGA, running all of this this code that I'm going through in JavaScript here as and this is a language I'm working on, an assembly language. It has a lot of the same characteristics of 6502, but a few more functions. Instead of branches, I'm using carry, and I have this patented ALU that I'm using on these. I have this arithmetic logic unit, and it was a very simple idea I came up with back in 1993. I got a patent granted for it in 2003. Took me 10 years and about $20,000 to get it patented. It's my first patent, U.S. patent number 6557092. You can go to the pto.gov and type in that number in a number search, and you'll find my ALU. And it's so simple of an idea. I took the full adder, and instead of doing the regular just hard coded add function, you got three inputs: your source A, source B, and carry bit, and you got two outputs. You got a carry input bit, you have a carry output bit, plus the result output for that bit column. And I thought, well, you got three inputs, two outputs. What if you put the three inputs on the selector lines of an 8-to-1 multiplexer? It's like a logic table. And I go, well, I have two outputs, so I need two of those with common selector lines. Source A, source B, and carry input bit. And the two outputs are carry output and result output, which is same bit column. So I came up with that idea in '93. Took me 10 years to get the patent. It's 2003. And then 17 years later, it ran its course, and now it's public domain. But I'd hesitate to use it if you're somebody like Apple that wanted to do it, because I'm working on my own doing this stuff. I don't have 1,000 people working for me day and night at one infinite loop, Cupertino, California. But yeah. And so I've been working on this for a while, and it's starting to come together. I've finalized this instruction set, and I have 32 registers, kind of a lot, all 24 bits wide. And then I have break, no operation with up to 256 cycles. I guess it starts at 1. Actually, 255 cycles or 0, which probably takes a cycle or two to register that it got a no op. But I don't know. And then we have the return from subroutine, jump to subroutine, jump, and then jump on carry clear, jump on carry set, jump to OS function, has a higher address, and then load register, and these A through Z are just generic registers. You use them for whatever. So we have program counter, stack pointer, carry history, overflow, remainder, and random number. And then there's a game console, so you need random numbers. Random numbers are useful, and it's a seeded random number, so you can program it to have a different sequence. And if you write to that, it programs it with a seed. And you can do seed on top of seed on top of seed if you want to. If you're doing something like encrypting a file, you don't want anybody to see it, and you have to seed it with the same seeds, or else you won't get the same random number sequence. And then and the rest are generic registers. Over here we have the same set as addresses. Instead of data, we're using them as addresses. And it goes through the same deal. Just got an A in front of it to say that it's an address rather than data. And then, so back to here. So we got jump to subroutine, jump on carry clear, jump on carry set, jump to OS, load register, store register, odd. Now this is something kind of cool that I haven't seen anybody else do. You got a number, and you don't know how many times 2 there is in it. So you want to make it odd so you can do things with that first bit, that first true bit. But it's somewhere up in the register somewhere. So odd takes this register, the middle one, and it shifts it right 1 bit at a time until it finds out that it's got a 1 bit. Either that or it's a 0 to begin with, and it needs to break out of it with a 0. So it counts the number of zeros on the right side if it's something other than 0, and it'll put that number in the, this could be whatever, it could be like G, for example. So it takes this I bit, this I register, and it shifts it right until it's odd, either that or it's 0. And it takes that number, and the result goes into Y, and G has the number of bits it got shifted over with. So it'd be something like this. There you go, 1 1 0 1 0 0 0 0, just for the sake of argument. So it would shift this right. It would shift it like this. It'd go boink 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 boink, and then it hits a 1, and that's the number that would go into Y. And then it would say 4 in G. It would have 4 in G. So I stays the same, Y gets this value, and G would have 4 in it for the number of bits it shifted it over. So yeah, I haven't seen that function anywhere. I think it's really useful, but it's just me. And then flip is something unique. Well, if we took the same thing we had before, we'd flip it. We'd go 1 2 3 4, and then we'd have 1 0 1 1. So it would take this. It would start with this value here, and it would flip it until it was like this. And so, flip. And it only has 2 registers. There's no reason to have a third. So there's a bunch of wasted bits, like six bits that it wastes. But no big deal. We've got plenty of room. And so that was flip. And then shift left. I got these 6 bits over here, and I'm going, what do I do with all these bits? I'm going, well, shift left. If you can shift left by 63 bits, let's give it the room to do so. And so it takes this G value, and it combines it with OV and RE. And so when you shift left, it takes G and shifts it, what is that, 72 bits? It's got a 72-bit shift register that shifts it over by 50 bits in this case. And then it puts the low value here, puts the medium value in overflow, and the high bits in RE. And roll left is the same deal, except it runs off the edge at 48 instead of 72. Don't ask me why, but 48. And so the high bits, see, we're doing all 63 here, so it takes all 72 bits, or 48 bits in roll's case, and rolls it around until the bits come back around to E, and it puts the value that came from E into AV, and the higher bits go off into overflow and remainder. And then so that's shift left, shift right, roll left, roll right, and then your typical AND. If A is true and B is true, the answer is true, otherwise it's false. And then OR. If A is true or B is true, or they're both true, then that's the value you get. We got 2 sources, and we got your source 1 and your source 2. And you do the Boolean on them, and it goes into result register here. So these are the two that are combined, and this is where the answer goes. In this case, is be the program counter. I don't know why you'd want to do that, but there it is, you know. And then here's exclusive OR, which is the same as OR, except in the case of the two source bits being true. It's also false. That's why they call it exclusive, because it's exclusive to the different bits. This or that. This or that, but not both, and not neither. So, if they're different, it's true. If they're the same, it's false. And then add. Binary arithmetic, it's complicated, but it doesn't add. In decimal, it would be the same sort of thing, except it would only be 1 or 0. It's like if you took tens and multiplied them somehow. Yeah, crazy. And then subtract, same deal. You're familiar with subtract, multiply, divide. Now these, I'm using the overflow again too. Multiply, it takes these two numbers, multiplies them together, and so if bits or digits are not numbers by themselves, they're digits. And so if you had in decimal, if you had 9 times 9, you get the answer 81. It's 2 digits for every 1 digit in the column. And so in the same fashion, S is S times ask. That's the address of the stack. This address, the data that's in the address that the stack points to, is multiplied by S, and the low end goes into AZ, and the upper end goes into OV, and so it's double the register size for multiplication. Now division works in a similar fashion. It takes these two numbers and the overflow, and it divides the overflow and AX combined together to form a 48-bit number. It divides by a 24-bit number to give you a 24-bit number. And I suppose the answer could potentially be greater than 24 bits, and so that would go in the overflow. And so we come out of the overflow, go back into the overflow. So if you want to keep the value that's in it, you have to move it somewhere else before you do the division. Same for multiplication. I think the multiplication can clear it safely. And then what else? So that's, and then modulus is just the remainder of a division. And so the remainder's got to be less than what you're dividing by. And you're going to start like with the divide, combined value. And then you're going to divide by this. The low number goes in here. The high number goes in overflow. And it's a modulus, so it's like the remainder after an integer division. And then nan, that's the opposite of and. It's confusing. So if A is true and B is true, the answer is false. Otherwise, it's true. That's a NAND. NOR is like OR, except inverted. So if one or the other is true, then the answer is false. If they're both true, the answer is false. But if they're both 0, the answer is true. Yeah, and then same, I call it. A lot of people want to call this exclusive NOR, but that doesn't really fit my definition for it. If they're the same, it's true. If they're different, it's false. So I call it same. And then ADC is the same as add, except we're bringing in the carry bit from the previous operation, the one right before it. And I have that all in the carry history. It keeps track of all the outputs of the 24 statements down the road. So every statement it puts a bit, either 0 or 1, shifted into the carry history. And then ADC, add with carry, subtract with borrow, square, square root, and factor. This one's going to be fun to write. I've already got a process that I'm thinking of that's quick. Be able to take 24 bits and break it into its, two different values. So it factors AZ and puts the result of the factor in AL and O. And so AL could be 1 if it can't find a factor, in which case O would equal AZ and AL would equal 1. And so I have I have a solution to Riemann, but haven't quite got it completely ironed out yet. But I'm confident. I have a thing posted earlier on a private YouTube that shows me going through some 9-digit numbers, 9 digits of decimal numbers, and factoring them within a second or two, under a second actually. And I'm going to go a little bit further with that, and we'll see how we do. But anyway, we cover a 24-bit number, no sweat. If I put that algorithm in Verilog, it'd be pretty quick. So then, yeah, these are my ALU. These all here are my ALU configured by the specified register here. FX is just function process or function cross, function of X. I don't know, but A is the A register. It's used as data here, as logic tables. It's used as logic tables, and so that goes in as the logic. That register in this column goes in as the logic, and this is the right or left. Tells you the direction of the carry. Does it come in from the top and work its way to the right down to the bottom, or does it start at the bottom and work its way up to the top going left? And then do we start with a 0 every time with the carry input bit, or do we start with a 1 every time with the 1 in the carry bit? And then we have V for inverted carry, and then we have C, which is the carry bit. And that's the low bit in carry history that gets shifted up with each instruction. And so it takes it takes source A and source B, combines them with the logic table in C, and then puts the answer in V. And then the output carry goes out to the carry history. So ALU, real simple, the thing we described earlier, the 3 selector lines on a pair of 8-to-1 multiplexers. The data on the multiplexers are provided by the register here. And so now we have video. So see if you can remember all this up here, because I'm just going to, and this stuff here. So If we hit the escape key, boom, we've got a clear screen. If we go refresh, so we have in video we have line, tile, frame, sprite, oval, and line if we can find it. Where's line? Give me a line. There's a line. So each of these have their own set of parameters. Sometimes it's an address. Sometimes it's direct data, like for color. Other times I have in here. Width and a height, both 12-bit numbers, so I can go up to 4K. 4K pixels horizontally. But I'm not going to be on 4K anytime soon. I got 720p working. Like I said earlier, this is a 720p resolution screen, and these are 16 by 16 bit or pixel tiles. And so I'm gonna have this all figured out pretty quickly. Probably before maybe January if I work at it, but maybe sooner. But here these are graphics commands to the GPU, and the GPU works independently of the processor. But I have a way of sending the GPU an instruction that goes into a FIFO, a first in, first out stack, and it does the operations kind of at the time they're issued. And so the processor has to be a little careful as to when it issues these, so there's not tearing in the image. But yeah, it could do these in the vertical refresh or something, and take care of them all up front right then. And then let's see, the audio is just volume, frequency, and a waveform. This is going to be an address. And this is probably just like a hard-coded number. You got two 12-bit numbers. So each of these are like going to be like stereo, and maybe I'll have like 8 voices, and each of these would be 5 bits. This instruction takes up 6. So 5 and 5 and 6 leaves what? Actually, this has got to be 6. So 6 and 5 would be, and then we'd have what? 2 bits left over. Maybe only 4 voices. Yeah. No. I could make this have to be you could make this have to be it would have to be an address, and so I have 3 bits left over, which I could have 8 voices for the audio, and something similar here. I have 8 primitives that you can issue to the graphics processor and alter the image and on the vertical refresh if you can time it that way. I can have an interrupt when the screen gets to the bottom of the page. It interrupts the processor and whatever it's doing, and it handles the graphics operations and then kicks back to what it was doing. And I can do that with a non-maskable interrupt or something. And then keyboard, I'm going to have a PS2 for this. That USB is just too complicated for me to figure out. I don't have the equipment or the time to mess with it. And same for the mouse, PS2, easy interface. And then input and output is going to be like to a line printer. Maybe maybe I'll be able to figure out how to interface with some printer stuff. But primarily, these are going to be for a SD card. Have an SD card for the storage. And so I hope I can get this I can get this code, GPU, CPU, input-output interfaces, television, audio, video, and have it all fit on maybe a $40, $50 FPGA, and then have an external memory like a DDR3 running at 400 megahertz. The whole 9 yards, 16 megabytes of 24-bit memory. I might have to put it on 3 different chips, to get the 8 by 16 megabyte that I need, and have that all work. I have this protocol. It's kind of an interesting idea. Error correction with serial interface. So that is something kind of unusual, because it would do this. It would have 3 bits at the top for stop bit, 3 stop bits, 3 stop bits, and next from the top it would be parity. Parity is going to have like a checksum. Parity is going to have a checksum of 8 bits. And then we're going to have 8 bits for the 1 register. And then we're going to have 8 bits for the 2 register. And then we're going to have 186 data bits. So 24 plus 186. So the 24 causes a 6 to be a 0, if you can get that. And then 80 makes it 200. Maybe there's more than that. Huh. 24, 200. Maybe it's more than that. But yeah, 186 data. Anyway, I got this all figured out in my head when I think about it clearly. But you take 256 bits and you break it into 7 times 24, and you do 6 of them are data, and the seventh is used as a checksum on 3 different categories of bits: the parity, the data bit, data 1 bit, and data 2 bit. And then so you get 6 24-bit numbers out of it with a parity. That's probably what it's going on. This is like what? there's 3 times this, sort of, in all this data. There's like and it works out perfect. It's like I keep losing my carry bit on that. So yeah, there's a way to do it. There's 256 bits. 256 bits of data. Use 3 for the stop. And then you have 7 times, 7 times, I have another problem. 7 times 24 bits of, let's give it a name. Let's give it a name like, what, GSC. Yeah, for a little bit of arrogance. GSC, the Guaranteed Serial Communications. Guaranteed Serial Communications. Gregory Scott Callan. Yeah, sorry. So, yeah, let's see. Yeah. So 3 stop bits. Three stop bits, 7 times 24 checksum. And then actually this is just 1 times. You have to be careful with the checksum. How about so this is 24 bits for checksum, and then we have 6 times 24 data. So is that gonna get it right? I think this is how it works. Let me think. Let's get the calculator out of my pocket. It's on the phone. So 6 times 24 plus 24 plus 3. And that gives us 171 bits. But it's all got parities in it. So for every 2 bits, let's round it off to 170. For every 2 bits, it does a third for the parity. So and it's for the whole number, and then so that's what, 85? Yeah. So if we have 3 stop bits, 24 bits of checksum, which is 3 bytes, 1 for each of the 3 data types. There's the parity, the 1 and the 2-bit. And then, so that's 3 bits. That's 3 bytes to say how many bits they are. And then 85 parity bits. For every 2 data bits, you have a parity bit. And that works out perfect to 256 bits. So, plus, let's go like this option. Command. Command. Shoot. And what do we got? 85. Parity. I'm spelling that wrong. Parity. Parity. So, yeah. So, I figured it out. It's perfect. It works great. And so, if there's an error anywhere in these bits, it's going to have a different, you got 2 high and 1 low, or vice versa, 2 low, 1 high. And so that's the parity bit that's going high or low, depending on which way the data goes. If the 1 and the 2-bit disagree, then the parity bit follows the 1 bit. And if they agree, then the parity bit is opposite the 1 and 2 bits. And so with that scheme, if there's an error, it's going to flip one of those bits the wrong way and indicate which packet had the error. And then with the checksum, you can go and correct it, because you're counting the 3 bits, the parity, the 1-bit, and the 2-bit. You're totaling them up in separate bytes, and that byte itself has also got the parity check on it, and so it's got it in the 24 bits as to which, you're going to get an error in the data, and then you're going to get a different number in the checksum, and then you're going to be able to go back and correct the bit without talking to the server and going, I lost a packet, I don't know what it should be. You just correct it and go on. With one-way communications. So let's see if that math works out. So you got, so you got 3 stop bits plus 24 bits plus 6 times 24, which works out to 171, but we're not concerned about that. And so if we do plus 85, 256 bits. Perfect. Isn't that cool?